All right, so we're going to kick back off here at section 4.7, and we started talking about conformational analysis during the last class, and it says here that the angle between atoms on adjacent carbons is called a dihedral angle. Sometimes we call it a torsional angle. The maximum space, or the maximum amount of degrees, I guess, that you could have between two hydrogens would be 60 degrees like that, right? 360 divided by 6. So we call that, again, a dihedral angle or a torsional angle. You'll probably hear me use both of them. But as we looked at last class, we said when we take an ethane molecule, we know that there's free rotation around the carbon-carbon bond, right? We have CH3, CH3, and we know that there is free rotation around this bond. And that's what's being shown here. We can have all of the hydrogens in the lowest energy conformation, and we call that a staggered conformation. And again, that's the conformation where the dihedral angle is 60 degrees, or we can have them in an eclipsed conformation, and that's higher in energy. It says here that the difference in energy between these conformations, right? The staggered is low energy, and the eclipsed is high energy. The difference in energy between these is based on what's called torsional strain. And it tells us here in the slide that the difference in energy between these two conformations, the eclipsed and the staggered conformation of ethane, is 12 kilojoules per mole. It's so great that when you have a sample of ethane, which is a gas at room temperature, that 99% of the ethane molecules will actually be in the staggered conformation. So if we look at the rotation around the carbon-carbon bond, we call that the conformational analysis. And we're going to look at a few of these today. We'll look at ethane, propane, and butane. On the y-axis here, we have energy or potential energy, and then here we have the dihedral angle. Now you notice that they've highlighted two of the hydrogens in red, and we start where these two hydrogens are on opposite sides of the conformation, so to speak. But then as we rotate, and the one that's being rotated is this hydrogen here, as we start to rotate that clockwise by 60 degrees, we see that we have an increase in energy, right? Because now we're going from staggered, right? All of these conformations are staggered, to eclipsed. And we said that eclipsed is higher in energy than staggered by 12 kilojoules per mole. And so if we rotate, and I'm not going to do this for every single conformational change, but we rotate this down again 60 degrees, okay, we end up having the hydrogen here. We move it down another 60 degrees, and you see that we keep going from low energy staggered conformation to high energy eclipsed conformation. Now notice that all of the eclipsed conformations are degenerate, and all of the staggered conformations are degenerate. What does degenerate mean? That's something that we talked about. Well, you would have talked about it in general chemistry, but we also talked about it in chapter 1 when we were talking about molecular orbitals and hybrid orbitals. Degenerate simply means the same energy. Okay, so all of the eclipsed conformations and all of the staggered conformations in ethane are all degenerate. They're all the same energy. Well, what happens if we analyze propane? Okay, what happens if we analyze propane? Well, we're doing the same exercise here. We're taking the propane molecule and we're rotating it down or on one of the carbon-carbon axes, right? All we're doing is we're analyzing this molecule, CH3, CH2, CH3, right? And we're just rotating around one of the carbon-carbon bonds. I could have picked this one, it wouldn't matter. It's the exact same thing. Let me show you by having my camera on here what it's going to look like. Can you all see my camera now?
Yes.
All right, so here's the propane molecule. I have CH3, CH2, CH3. If you look down one of the carbon-carbon axes, okay, and if I put it in a staggered conformation like this, you can see that I have the methyl group up here off to the side like this. All the dihedral angles here are 60 degrees. If I rotate it by 60 degrees, then you see that the methyl group is now eclipsing this hydrogen. If I rotate it another 60 degrees, now you can see that it's staggered again. If I rotate it another 60 degrees, I have another eclipsed conformation, and the methyl is blocking a hydrogen. And I can keep doing that every time I rotate it by 60 degrees. I go from staggered to eclipse. And that's what we were seeing in that conformational analysis in the slides. So this is exactly what we're seeing here. And you see that there's a difference in energy between the staggered conformation. So these are all staggered. Okay, these are all the staggered. And these are the eclipsed conformations. You see that the difference in energy here is a little bit higher. For ethane, it was 12 kilojoules per mole. But now for propane, it's 14 kilojoules per mole. And so we can clearly see that the interaction between the methyl and a hydrogen, whenever they're staggered, it must be higher energy than when we simply have two hydrogens eclipsing each other. If we evaluate that, okay, that barrier of rotation, that 14 kilojoules per mole, we see that it's 2 more than ethane. Let's go back to the ethane for a second here and do some very quick math. Okay, if all of these staggered conformations are 12 kilojoules per mole higher in energy than the eclipsed conformations are 12 kilojoules per mole higher in energy than the staggered, that means that each one of these 1, 2, 3 hydrogens that are eclipsed, each one of them must cost 12 kilojoules per mole divided by 3, which would equal 4 kilojoules per mole. So that means that every time 2 hydrogens are next to each other like this, it's going to cost you 4 kilojoules per mole. Let's go back to our propane. If you look at any of the eclipsed conformations of propane, you see that you have 1, 2 hydrogen-hydrogen interactions. Both of them cost 4 kilojoules per mole, but the total is 14. So 4 plus 4 is 8. 14 subtract 8, and what do you get? You end up with 6 kilojoules per mole for the hydrogen and methyl interaction. So it's a higher energy than just the simple HH eclipsing interaction. I'm not really going to ask you to quantify these things on a quiz or anything like that, but you should understand the rationale. Now, if you look at the conformational analysis of butane, it's even more interesting than that of ethane and propane. And the reason why is because if you look at all of the staggered conformations, these are all staggered, all at the bottom. And if you look at all of the eclipsed conformations, you see that they're not all degenerate, right? You see that you have these two that are degenerate, but then you have this one that's higher energy. The same thing applies for the staggered conformations. You see that you have this one, which is the same as this one, anyhow, which are lower energy than these two right here. There's got to be a reason for that. Well, when you analyze it, just by looking at the conformational analysis, I think it's pretty clear. But in case it's not, let me show you using a model. So I'm going to go back to my camera here just for a second. Let's see here. Give me 2 shakes of a lamb's tail. I'll get it set up. Okay, so here's my butane molecule. Here it is. I have CH3, CH2, CH2, CH3. You see how I have it in the zigzag? Just the same way you would draw it. So we're going to look down this carbon-carbon axis between carbon 2 and carbon 3. When we look down that axis, you see that everything is staggered here, but you see that the 2 methyl groups, the 2 CH3s, are as far away from each other as possible. If I rotate that to the next staggered conformation, it is staggered. All the dihedral angles are 60, but it's different than the last one because the 2 methyl groups are next to each other. Okay, and we have a name for these, and I'll talk about that in a second. But you see, if you rotate it again to the next staggered conformation, you also see that the methyls are close together. So that's why when we analyze the staggered conformations, 2 of them were higher energy than 1 of them. Okay, 1 of them was lower energy, and that would be this one here. The same thing applies for the eclipsed conformations. If I eclipse it like this, okay, you can see that this eclipsed conformation and this eclipsed conformation are going to be lower in energy than the eclipsed conformation where both of the methyl groups are blocking each other, right? You can see there's going to be some steric hindrance because these 2 hydrogens are very close to each other in this eclipsed conformation. Now, if you don't quite follow me on my models, let's go back to the slide and see if we can clear things up there. Okay, we're back on the slide now. Let's again analyze the three staggered conformations. Now, when the two methyls are as far away from each other as possible, you can see that those are lower in energy than when the two methyl groups are still staggered, but they're close to each other. And there's a name that we have for that interaction. I'm going to talk about it in a second. You can see that the cost of energy is 3.8 kilojoules per mole. If we look at the three eclipsed conformations, again, you can see the one where the two methyl groups are eclipsed next to each other. That's going to have a higher cost in energy as well. Okay, now getting back to some terminology here, and we're going to start with the staggered conformations. When the two methyl groups are as far away from each other as possible, we call that an anti-conformation. Okay, anti, the methyl groups are the furthest apart. Those two other staggered conformations, but where the methyl groups are close together and where there's going to be some blocking, right, it's what we call steric hindrance, we call that a gauche conformation. Okay, a gauche conformation. So you need to know the difference between an anti-conformation and a gauche conformation. Now the whole thing here, it says the stability of the different staggered conformations differs by 3.8 kilojoules per mole. Again, I'm never going to ask you to memorize these numbers and to quantify anything. You just need to understand the rationale as to why these two would be higher energy staggered conformations than this one. And it's simply because of the steric hindrance, right, of these big methyl groups coming close to each other. They're saying, quit crowding me, bro. You're taking up my space, right? So an anti-conformation is going to be lower in energy. Let's move on from there. All right, give me a thumbs up if you follow me on conformational analysis. Even if you're just thinking, you know, Mr. Dion, I need to spend some time studying it, but I think I can figure it out. Anybody with me? Okay. All right. Thanks, Moira. Great. All right. Thanks, Megan. Good. Okay, well, let's move on to cycloalkanes. You know, I've taught a lot of students organic chemistry over the years, and I've seen them come up with all kinds of memes. And one of the memes that keeps coming up in organic chemistry are things I learned in organic chemistry was how to draw hexagons. And there's a reason why that's such a popular meme in organic chemistry. And I'm going to explain that to you today. Namely, and we're going to start with this section here about cycloalkanes, right? Remember we started naming cycloalkanes? You go from cyclopropane to cyclobutane to cyclopentane, cyclohexane, cycloheptane, cyclooctane. Well, when chemists first started studying cycloalkanes, they knew several several compounds that contain 5-membered rings and 6-membered rings. They didn't have any compounds in the 1800s with 3-membered rings or 4-membered rings, even though we know it's such a thing right now. But what they proposed is that cyclopentane would be the most stable of all the cycloalkanes. And the reason why is because, and that's wrong, but I'll explain why they thought that. Because they said, well, if you look at the angle in cyclopentane, a pentagon, when it's drawn on paper, the angle is 108 degrees, and that's closest to a tetrahedral angle, right? A tetrahedral bond angle, which is 109.5 degrees. So this is analysis in 2 dimensions, right? But we know that molecules aren't 2-dimensional. They're 3-dimensional. And so if a ring was flat, then all of the carbon-carbon bonds would be eclipsing each other. Now, I'm not going to go into that in gross and dirty detail. When we look at cyclobutane, I'll show you why that is. And in cyclopropane to some degree. But that would cause a crazy amount of torsional strain. And so the bottom line is that cycloalkanes try to they do everything in their power to not be planar, right? Because when they're planar, that's going to be high energy. Now, if we want to compare the energies, right, the relative stabilities of all these cycloalkanes on here, how would we do it? Well, if you go back to last class, we talked about the stability of alkane isomers, right? We said that the more branching you have on an alkane, right, we said the more stable it is, and I went over that in terms of change in enthalpy based on combustion. Well, if you were to cause each one of these cycloalkanes to undergo combustion and compared all of their delta H's, okay, all the changes in enthalpy for combustion, that wouldn't be a fair comparison, would it? Because here you have 3 carbons, here you have 4, here you have 5, so on and so forth. So what we do to make a fair comparison is we compare the heat of combustion for each one of these cycloalkanes and more, and then we divide it by the number of methylenes, and a methylene is a CH2. Right, we've learned that a CH3 is a methyl, a CH2 is called a methylene, and a CH is called a methyne. So I'm going to try to stop saying CH2s and CHs. They're called methylenes and methynes. Well, let's take a look at what the heat of combustion per methylene group looks like. So here it is in table form, okay, for those cycloalkanes, starting with cyclopropane, right? That's cyclopropane. Then we have cyclobutane. Then we have cyclopentane. Then we have cyclohexane, so on and so forth. And you can see that when we compare the heat of combustion per methylene group, that cyclohexane, wow, is by far the most stable. Right? It's the most stable. You can see that cyclopropane is very unstable, and there's a good reason for that too. But the reason why cyclohexane is so stable compared to the rest is because of the bond angles when we look at the three-dimensional structure. Well, let's take a couple of seconds and talk about cyclobutane very quickly. If you go in the book, he talks about cyclopropane. So this is cyclopropane here. I'll just mention it quickly that the reason cyclopropane is just so stinking high energy, and if you're wondering, does it exist? Yeah, it exists. But the reason why it's so high energy compared to the rest is since all of the carbons are sp3 hybridized. I mean, you think about what you would have to do to get these orbitals to overlap. I mean, they try to go out of the bond plane here, but they're still so strained in this overlap that it just makes it really high energy. If we move up to 4 carbons, though, and we look at cyclobutane, which again in 2 dimensions is just a square like that, but if we look at the 3-dimensional structure, it says here the cyclobutane is 27 kilojoules per mole less stable than cyclohexane per methylene. So it's quite a bit. It says it's got bond angles of around 88 degrees. And because of the slight torsional strain from the adjacent carbon-hydrogen bond, so you have torsional strain here, you have it here, so on and so forth, it's not fully eclipsed and not fully staggered. Now, I can't make a cyclobutane molecule with my model kit. If you try, it'll break it. But what it does is it adopts this kind of puckered conformation. You see how it's kind of indented like this? And it does that to try to alleviate some of that torsional strain. Now, if you're wondering, what do I need to know, Mr. Dion? All you really need to know is that cyclopropane is the most strained of all. It's the highest energy. And then cyclobutane, it drops down from there. Well, when we get down to cyclopentane, I can make a model of that. It says there's very little angle strain. The bond angles are close to 109.5 degrees, but it does have some torsional strain, and it adopts this envelope conformation, what we call an envelope conformation, to try to alleviate that. Son of a gun, my model's like snapping here. There we go. Just give me 1 second, and I'll show you a model of cyclopentane. Let's go back here. All right, so here's a model of cyclopentane. Okay, you can see it looks just like a pentagon here. And if it was flat, see, I have it so that it's planar like this. You can see that would be really high energy. I mean, look down any of the, so look, let's look down this carbon-carbon bond. Look down. Everything is eclipsed. Let's look down this carbon-carbon bond. This one here and this one here. Look, everything is eclipsed. Trust me, if you look down all of them, everything's eclipsed. But it's not planar. It says that it adopts an envelope conformation where the top kind of folds over like an envelope, like that. And what happens when you do that is it alleviates some of that strain. Now you look down that bond, and it looks like it's almost staggered, right? If you look down this bond, it looks like it's, I'm trying to hold it up here, it's almost staggered. Now you might be thinking, well, what about these two, Mr. Dion? These are going to be eclipsed. Well, what it does is the envelope, and you're going to have to forgive me, I'm doing my best here to show you without being in the classroom, but the envelope will point up here, and then it rapidly changes, okay? So it keeps dancing around, if you will, or the pointy part of the envelope keeps switching carbons, and that way it alleviates some of the strain. Before I go back to the slides, I just want to put a 6th carbon in there because you're going to see the most beautiful thing ever. When we put 6 carbons in a ring, okay, this is why cyclohexane is such a large focus of this chapter. Here's your hexagon. You see that every carbon in the 6-membered ring has 2 hydrogens, okay? They all have 2 hydrogens. It looks like a hexagon there, but when I turn it on its side, like this, you see that every carbon is perfectly tetrahedral. Every bond angle in the cyclohexane model is 109.5 degrees. This angle, there is no angle in here that is not 109.5 degrees. Since every carbon, all 6 are sp3 hybridized, that is the answer. That is why cyclohexane is the most stable of all the cycloalkanes. Let's go back to the slides, and I'm going to come back to that model in a little bit. All right. Come on. There we go. Okay, so let's go to cyclohexane. Now again, I told you that cyclohexane can adopt the conformation where all the bond angles are 109.5 degrees. That's called the chair conformation. So all angles 109.5 degrees. But the thing is that the cyclohexane can adopt other higher energy conformations as well. The only ones you're really going to be concerned about in this class are 99.9% of the time will be the chair, okay? And you can see why it's called a chair, because you see the person sitting in the chair right here. The other one that will come up from time to time, you know, might be worth a question or two on the next quiz, would be the boat. And you see that the boat is considerably higher energy. And the reason why is because we get what are called flagpole interactions by the hydrogens here and here. They really get close to each other and makes it higher energy. Now you might be wondering, what the heck is all this other stuff, Mr. Dion? A half chair, a twist boat, another twist boat, another half chair. Okay, I'm not really going to ask you about a half chair or a twist boat. The reason that Dr. Klein put this figure in our class's textbook, even though it's an introductory course, is for you to understand how you go from a chair to a boat. Now, you've heard of the song From a Jack to a King, but you've never heard of From a Chair to a Boat. Where am I? All right, so we have our chair, right? Son of a gun. Where's my chair? Here's my chair. I should have got one of my daughters like Barbie dolls or something. I could have sat it in the chair maybe. Anyhow, I put the chair like this, okay? And then I can have the boat is when you flip up like this, but you can see why the boat is higher in energy, because you have these two hydrogens interacting with each other, okay? So there's the boat. Then if you twist it, that's called the twist boat. Here's the other twist boat. This would be the half chair, which is actually hard to make with these models, but you get the idea. Anyhow, you can see why models are really great in organic chemistry. Go back to our chair. The next thing we're going to look at, I think in a second here, if I remember my slides in order correctly, is we're talking about flipping the chair. And I mentioned this to you at the very end of last lecture. Let me get a different colored atom here from the box. If I have this red atom in this position, when we talk about flipping the ring, if you read the book, and I hope you all did before coming to class, it doesn't mean you're flipping it like a pancake. It means that you're doing a conformational change where you rotate every carbon-carbon bond in the molecule by doing this. So like you pull this down, pull this up. So now my red group is still pointing up, but it's not pointing straight up. It's pointing up and off to the side. We call that equatorial, okay? Watch, you're going to flip it again, okay? And now it's up and it's in a position that we call axial. So that's a ring flip. Watch, flip like that. It's almost like those transformers. Is that still a thing? I don't know. Anyhow, you see, flipping the ring. It's not flipping it like a pancake. It's a conformational change. And what's going when I flip it very quickly is all of the carbon-carbon bonds are rotating. That's why these models are so great. They're expensive, but they're great for showing ring flips. All right. Anyhow, where was I? Let's go back to the slides here. Does anybody find that useful when I show you the models?
Absolutely.
Okay, good. Thanks for telling me, because I don't want to waste my time going back and forth. If you're like, I can just look at the book, Mr. Dion. I got it straight. Good. I think, you know, showing the models, to me, it helps. You know, when I was in graduate school, I worked on Decalin systems. So Decalins, when you have, and this is nothing you need to know, but it's when you have two cyclohexanes fused like this, and you can have them what's called cis and trans. And I used to get really confused about them when I first started. And then my supervisor was like, here, take these. And then, you know, give me, after an evening of messing around with the models, I had it figured out. So I think there's something to be learned from models. Anyhow, going back to the cyclohexane, so I'll erase this. Going back to the cyclohexane, it's got no ring strain in that chair conformation. I promise you that all bond angles are perfectly tetrahedral. There's no torsional strain. If you look down these two bonds, so this is like you take your eyeball number 1, eyeball number 2, okay, and you look down both of these carbon-carbon bonds. And you can tell I'm getting excited because this is interesting, okay, it's fascinating. You look down both of those and you kind of do like a double Newman projection. Look at this. Everything is staggered in there. Everything is perfectly staggered. So no angle strain, no torsional strain, no ring strain. That is why cyclohexane is so stable. Okay. Hopefully you got it. You know, you understand just the concept at least. That's why it's so stable. Now, drawing chair conformations. Now we are in a pandemic, in case you didn't know. And normally, when I gave a quiz on chapter 4, I would always put a minimum of 2 questions on our paper quizzes where I would get my students to draw a cyclohexane. Okay, it's a draw a cyclohexane. It was always murder grading it because usually some of the students aced it, you know, figured it out really quick. Other students would struggle with it. Even though our quizzes are what do they call multiple choice, I recommend still learning how to draw a cyclohexane. I know some students use these templates, and I think you could use that, I suppose. But to learn how to draw a cyclohexane is a helpful thing. Okay, you need to learn how to draw it in both conformations. And Mr. Dion's not the world's greatest cyclohexane drawer, but there's one conformation, and if we flip the ring, then it's going to look something like that. Okay, so there's my 2 chairs. They're good enough. I'd never seen this at all until I moved to the United States and saw Dr. Klein. Yeah. Is she asleep? I can hold her. Could I put her on the ground? Okay. Sorry about that. Anyhow, where was I? If you want to use this technique for drawing a chair, feel free to do that. There's no problem. Skylar, I would normally lecture holding the baby, but I can't do it today because I need to go back and forth to my models. Anyhow, my wife needs to take the kids to school, so she wanted me to take her. Anyhow, where the heck was I? So drawing a chair. If you want to use this technique, by all means, go ahead. I don't really care how you learn how to draw a chair. I just want you to learn how to draw it. Okay, so I recommend practicing. You can use David Klein's technique. It totally works. You start with the wide V. You draw a line coming down in this direction. Then you have a series of parallel lines. But the way that I did it, the way that I learned it was working in a carbohydrate lab, and all you do is draw cyclohexane, draw chairs and boats all day. But you notice that there's 3 sets of parallel lines, right? I have 2 parallel lines here. I have 2 parallel lines here. And then you have 2 parallel lines there, right? Same thing, 2 parallel lines here. You guys know parallel lines? Blondie? No? Anyhow, you got 2 parallel lines here. All right. Anyhow, so you've got 3 sets of parallel lines. Again, and I've discussed this with Dr. Anderson, and he teaches organic chemistry too. I say, what do you do? He says, I don't know, whatever the students want. Just it's a good idea to practice drawing a chair. Okay. Again, if you draw it correctly, it should have 3 sets of parallel lines. Now, on each carbon, right? Each carbon is tetrahedral. So that would mean on each one of these carbons, there's 2 hydrogens. Now, there's going to be one pointing up like this and one pointing down like this. The up position, whenever you have something going straight up or straight down, we call that axial. And whenever you have something going down or up, but it's not going straight up or straight down, we call that an equatorial position. Now, how do you draw the axial and equatorial position? The equatorial position might seem counterintuitive, but it's actually a little simpler to draw. If you look at this bond here, you notice that it's parallel to these 2 right here. The axial position goes like this. The axial is either going to be straight up to the moon or straight down below, okay? So if you follow these 2 bonds, you see how this bond is going on an upward slope and this bond's going on an upward slope? So then you go straight up, and that's your axial. Let me show you again. Let's say I was drawing, the axial and equatorial position at this carbon I have circled in green. Look, my equatorial position is going to be parallel to these 2 lines. Okay, so it's going to look like this. And my axial position, you see how both this bond and this bond are on a downward slope going towards the carbon. Therefore, my axial position is going to be straight down like that. Okay, so you can practice that over and over. You got to practice adding axial substituents, and you've got to practice adding equatorial substituents. Now, again, this is one of those sections of the class where it's kind of strange. I could sit here and lecture on this to you, at you until 9 o'clock. Okay, we could spend the next 30 minutes just talking about this. But until you sit down by yourself, I've taught it enough to know, until you sit down by yourself with a piece of paper, just take a couple of blank sheets of paper and practice drawing chairs, you will master it. Okay, you will get good at it, but it takes practice. So just hearing me talk about it isn't really getting you that much practice. Anyhow, so let's talk about it a little bit more though. And you see how the axial substituents, you have 3 of them that are pointing straight up, and you have 3 of them that are pointing straight down. And notice that they alternate, right? You have up and axial, you have down and axial. You have up and axial, you have down and axial. You have up and axial, and you have down and axial. Look at the equatorial groups, all the ones that are highlighted in blue in this model right here, okay? You notice that this one is pointing down and is equatorial. This one's pointing up and is equatorial. This one's pointing down and is equatorial. This one's pointing up and is equatorial. This one's pointing down and equatorial. And this one's pointing up and equatorial, like that. If you need to see it in a model, okay, let me show it to you. So let's take a little pause here and go back to the model. Where am I? Here's my cyclohexane. And again, I recommend getting a model kit. They don't cost much. You can buy one from Jeff Bezos for not a whole lot. You guys know who Jeff is, right? Anyhow, he's the richest man in the world, or he was. I think Elon took him over, right? Anyhow, we have our cyclohexane here. Okay, beautiful cyclohexane. Look, if I try to hold it like this, so you can see the chair, you see you have 1, 2, 3 groups pointing up and axial. You have 1, 2, 3 pointing down and axial. Look at the equatorials. They go down, up, down, up, down, and up. So they alternate, okay? They alternate. Look what happens when I flip the ring. And I've showed this to you. This is the 3rd time, but it bears repeating. If you have a substituent, okay, let's pretend that this is an oxygen. Okay, if you have an oxygen coming off here, that would be a hydroxyl, it would be an alcohol, right? But if you had an oxygen coming off here like this, if it's up and axial, whenever you flip the ring, it's still going to be up. Okay, no matter what you do to the ring, if you flip it to the other conformation, it's still pointing up, but now it's up and equatorial. So up and equatorial, I flip the ring, it's up and axial. Okay, even if I turn it over like this, okay, here it's down and axial. If I flip the ring, it's still down, but now it's equatorial. Okay, so that's up and axial, up and equatorial, down and equatorial, and then if I flip the ring, now it's down and axial. Okay, so that's the models. All right. Anyhow, you got to practice. You really have to practice manipulating things in your mind in organic chemistry. All right, and we're going to get even more practice on this in chapter 5. Not necessarily conformations, but in the next chapter we study what's called stereochemistry, which is the relative position of atoms and groups in space on a molecule. My best friend, his sister is in dental school right now, and when she was studying for the dental exam, one of my former students who's in dental school right now, he gave me all of his DAT study materials. So you have to write the DAT if you want to go to dental school. Anyhow, he gave me all his DAT materials, and there's one called the DAT Destroyer. I was looking through, of course, what am I interested in? The organic chemistry section, right? So I went straight to the organic chemistry section. And one of the things they would do is they would put up a shape, okay? And then, and it was just a word problem, this is just on paper, but it would give you some kind of weird shape, and it would say, rotate it 180 degrees clockwise, rotate to the back, to the left, this many degrees, and rotate this many degrees. Is it A, B, C, or D, right? Which one of these would you be seeing? And I thought, it's kind of an interesting question. And his sister said, well, the reason why they want you to be able to manipulate things in your mind very clearly is because when you're, let's say you're, working on somebody's teeth, she said, oftentimes you're looking at a reflection because you're using a little mirror there, and you're just using that. If you're working on the back of somebody's tooth, you're not standing on their uvula or swinging from it like Miley Cyrus, you know, you're actually looking at a mirror image. And so you have to kind of be able to work backwards, something interesting there. Anyhow, so you can see how this is a useful skill. Also, if you wanted to be a plastic surgeon, I suppose you'd have to be able to manipulate things in your mind quite well and have some artistic abilities. Anyhow, let's get back to the monosubstituted cyclohexane. I showed you this, that when this substituent is up and axial, that when you flip the ring, it's still pointing up, okay? But now it's equatorial. Anyhow, rim flipping, again, this is probably the 5th time I've said this. It's not like a pancake. It's actually rotation around all of the carbon-carbon bonds in the molecule. If you don't believe me, get yourself a model kit, give it a try. The models that I have are called Feezer models. I wouldn't recommend buying them because they're so expensive, but if you won the lottery or something, you might buy some. Anyhow, all right, give me a thumbs up if you follow me on the concept on axial, equatorial, up, and I flip the ring, substituent is still up. If something is down and I flip the ring, it's still down. It's not a pancake flip. All right, excellent. Thanks, you guys. Good, that's great. That's wonderful. Okay, well, let's talk about this monosubstituted cyclohexane. What if we just had a methyl group? Okay, that would be called methyl cyclohexane. We talked about nomenclature. You guys know the name of the molecule, right? If I drew it in 2D today, okay, this would simply be called methyl cyclohexane. Well, now you know that this carbon has an equatorial position and it has an axial position, doesn't it? Yeah, absolutely it does. Well, you see that when you study both chair conformations, you'll see that at room temperature, the methyl cyclohexane, where the methyl group is in the equatorial position, is more stable. It's in the more stable chair 95% of the time. The more stable chair is the one where the methyl group is equatorial. So more stable, and you can tell that from the equilibria, right? It's more to the right. Anyhow, you might be wondering, why the heck would that be? It's based off of sterics, right? It's based off of size, okay? And look at this. Now, in case I bet you there's some people who have had it figured out, right? There's a hydrogen pointing up here, and there's a hydrogen pointing up here. When I write it with my Apple pencil, it doesn't look very big, does it? No, it doesn't look very big. But if you make a model, you can clearly see that there is an interaction between that methyl group and the two hydrogens. Let me prove it to you, okay? So let me go back to my models. Where are my models? Okay. Let's see here. Okay. So if I put, they updated the iPad and now there's 2 buttons you have to push. Anyhow, here we go. So here's the methyl group. I'll take that oxygen off. Here's the methyl group. It's up and axial, okay, in my chair, okay. Now, when I rotate it here, it's in the equatorial position. And if you looked at any of the axes in the equatorial position, it's always staggered, okay, it's always staggered. It's staggered here too, if I looked at any of the axes, right? It's staggered in this position as well. The problem is this. You see my methyl group? I'm going to try to get out of the picture. You see my methyl group? It's close to these 2 hydrogens here, okay? And we call that, since you go 1, 2, 3 carbons, or 1, 2, 3 carbons, since they're 3 carbons away, the methyl group and the 2 hydrogens, we call these, ready for it? They're called 1,3 diaxial, because this is axial, this is axial, this is axial, this is 1,3 diaxial interactions. So that's the reason why it prefers to have the methyl group in the equatorial conformation. Now, 1,3 diaxial interactions is a really sassy thing. Makes you sound really smart. But as long as you understand that it's a steric strain, right? You should know the name, 1,3 diaxial interaction, but it's because of the size, right? It's just too dang big. It gets close to the axial hydrogen there, and it gets close to this one here. Again, you have 1, 2, 3, or 1. Can't see the carbon in the back, but the 3rd carbon would be over here. Okay. What the heck is a 1,3 diaxial interaction? The 1,3 diaxial interaction is nothing more really than a gauche interaction. Okay. You don't have those 1,3 diaxial interactions when the methyl group is in the equatorial position. They're just gone. Okay. So that's why it prefers to be in the equatorial position. So the next question, right? Organic chemistry is like you're unfolding a story all the time. Well, I bet you there's somebody who's thinking right now, well, come on, Mr. Dion, what's going to happen if I replace the methyl with something even bigger? What if I put a tert-butyl group there? Is that going to have a bigger effect? The answer is hell yeah. Okay, of course it's going to have a bigger effect because it's bigger. The 1,3 diaxial interactions will just be stronger, and so it's going to prefer to be in the equatorial position, right? 10,000 to 1, right? 999,000 to 1. Whereas in the methyl, we said it was only 95 to 5. It only prefers to be in the equatorial position 95% of the time. You don't have to memorize these ratios. What you should know, though, and I'm asking you to memorize this, is you should know the order that we go from a chlorine is pretty small, then to a hydroxyl, then to a methyl. And the last four, I think, are very intuitive. If you go from a methyl to an ethyl to an isopropyl to a tert-butyl, yeah, the effect should become more pronounced. Let me prove it to you if you don't believe me. Let me go back to my camera again. And let me get a few more atoms here. Up and atom. All right. So let's see here. Here's just a simple methyl group, CH3. Yes, there are some 1,3 diaxial interactions. If I put another methyl group on there, here we go. Okay, look at that. Yes, there's free rotation around this bond. Yeah, the ethyl group could be over here, but there's also free rotation. And if that methyl group is over there, look at that. Look how close it is. These two hydrogens. Are you kidding me? Of course that's going to be higher energy. What's going to happen if I toss another methyl group on there? Right? Then the odds are even greater that I'm going to have a methyl group. Like, look, yeah, it could be in this conformation. Yeah, it could get away, but there's even a greater probability that they're going to be crowding it. And look what happens when you throw a third one on there. Then you've got a tert-butyl group on the top, right? Carbon, CH3, methyl, methyl, right? 3 methyls. That's a tert-butyl group. I mean, first of all, it's just so big. I mean, look at it. But look, there's no escape. There's no escape. There's always going to be that 1,3 diaxial interaction, okay? It's just always there, all right? And the reason chlorine is smaller is because chlorine is not as big, right? If I put an oxygen in there, yeah, there's a 1,3 diaxial interaction, but it's not as big. Okay, it's not as pronounced. All right, give me a thumbs up and follow me on that concept. All right, good, good. Not a simple concept, right? It's not a joke. It's no joke, but it is logical. At least I think it is. Anyhow, there we go. Now, what happens next? What if we have 2 substituents? Well, it gets even more interesting. Okay. Now, considering that we can have 2 conformations for our cyclohexane, right? We can flip the ring. That's what I mean by the 2 conformations. Remember, I showed you a chair drawn this way, and then I showed you a chair drawn the other way. So let's analyze this compound here. Now, remember that when we have a wedge, that means that the chlorine is pointing up. And when we have a dash, that means that the methyl group is pointing down, right? In organic chemistry, sometimes we don't just use CH3, we use Me to represent a methyl. Same thing with an ethyl. Instead of putting CH2, CH3, sometimes we just put ET. It means the same thing. And for propyl, we just put PR. For isopropyl, we put IPR, like that. Anyhow, there's a few of them, and you'll see them along the way in the class, right? Organic chemists are notorious for wanting to get the maximum amount of work done for the minimum amount of effort. We're not lazy. We just work smarter, not harder, right? Anyhow, look, let's stop for a second. Slow down. This chlorine is pointing up. You all agree with me with that because you agree with me on that because it's a wedge. This methyl is pointing down. You agree with me on that too because this is a dash. Well, hold the phone. Just because this is up, does it mean it's equatorial or does it mean it's axial? I told you that equatorial and axial can both be pointing up. Just because this is pointing down, is it down in axial or is it down in equatorial? Now the answer is right here. But I want to make a model and show it to you. Okay? Before we do that, it says realize that the chlorine is up in both possible chair conformations and the methyl is always down. So if the methyl's down, it's always down. If the chlorine is up, it's always up. Look at this conformation first. Here we have the chlorine is up, but it's up and axial. Here we have the methyl group pointing down, but we know that on the next carbon that the axial position is going to be the down position. So both groups are axial. If you look at this one over here, this conformation, you can see that the chlorine is up, but it's up in equatorial, and the methyl is down, but it's down in equatorial. let me show you what happens when you make the model. And I'm sure that most of you are just like, yeah, get on with it. I get it. But I'd just like to show you with a model quickly, very quickly. So we have a chlorine. Let's pretend that this this red atom is a chlorine. And I'll get my methyl. Just give me 2 shakes of a lamb's tail. So I'll try to do it like they have it. So you get the chlorine pointing up, and then you have the methyl. So we're going to do it like this. So you have the chlorine pointing up, and then you have the methyl group pointing down like this. Okay. So here in this conformation, you can see that the chlorine is pointing up and axial. You go to the next carbon. The methyl group is pointing down and axial. Now watch what happens when I flip the ring. Poof, like that. Okay. The chlorine is still pointing up. Okay, but now it's up in equatorial, and this methyl, it's coming straight for you, but it's pointing down. It's down in equatorial. So flip, up in axial, down in axial, flip, up in equatorial, down in equatorial. Okay, I know it's kind of hard for me to manipulate this. I'm not an expert, showing things on a camera, but hopefully that clears it up for you. All right, where was I again? Okay. Get back to it. There we go. Let's move on from there. So with that in mind, let's try a practice problem. Okay. It says draw both conformations, both chair conformations for the following molecule, and which one is more stable. Now, before we do this problem, there's more than one way to draw a chair, okay, to represent a molecule in a chair. It depends on what carbon you start on. So when you look at the answers or the solutions in the solutions manual, yours might not look exactly like theirs, okay, but you can still be right. And I'll try to explain that here. I'm going to start by drawing 2 chairs, and I'm going to show you kind of the convention that I use. Since I teach this for a living, I've tried to develop some conventions to try to keep things simple with my students. So look, I'm going to start by drawing a chair with this conformation. So I'll put my chair here. Okay, and then I'm going to draw the other conformation. So that's going to be like this, like that. Okay, if you draw this, a bow tie, that is not correct at all. You cannot, it's impossible to grade that, Back when we did paper quizzes and somebody drew a bow tie, I can't tell what the hell is going on with that. Okay, so what I try to do, and I probably don't do this all the time, but I try to do it like this. I go 1, 2, 3, and this is just Mr. Dion's convention. You can start on, you can call any carbon you want carbon 1, doesn't matter. But again, just because I teach this for a living, I've tried to do this where I'll label this carbon as carbon 1, and then I go clockwise, so 1, 2, 3. Okay, so if the ethyl group is pointing up, and I'm going to highlight this carbon in yellow. Okay, will the ethyl group be, my question to you is, I'm dead serious, will the ethyl group be axial or equatorial in this carbon that I have highlighted in yellow on the chair? Will it be axial or equatorial? That's my only question.
Axial.
Axial, son of a gun. Absolutely, right? Because this bond is going up in this direction, and this bond is going up in that direction. And so the up is going to be in the axial position. So we'll put our ethyl group. CH2, CH3. There's our ethyl group. Now our methyl, it's going to be pointing down. So it's going to be on the carbon that I'm going to highlight in green. Okay, it's going to be pointing down. So on carbon number 3 in my chair, will the methyl group be pointing up? Or sorry, will it be, and of course it's going to be pointing down, but will it be axial or equatorial? That's my question to you. Will the methyl be axial or equatorial?
It'll be axial.
Okay, I got a 50-50 split. Okay, it's going to be equatorial. And the reason why is because you have this bond going up in this direction and this bond going up in that direction. That means that the axial position is the one that's pointing up, and that's got a hydrogen on it. Since the methyl is going down, okay, since the methyl is going down, it's going to be going down in this direction, like that. There's my methyl group, CH3, okay? We can fill this in, CH2, CH3, okay? Again, you see how the equatorial position is parallel with these two lines right here. Now, of course, you're learning this, okay? But hopefully you've tried it before class. But anyhow, you need to practice or recognizing equatorial and axial position. So now what I did is I flipped the ring. Okay, so this is just an equilibria. And I flipped it, not by flipping it like a pancake. I rotated the bonds. And so what was carbon 1 there is carbon 1 here. So now I've got 1, 2, 3. So if my ethyl group was up and axial in the first conformation, it's still going to be up, but now it's going to be up and equatorial, right? This would be the axial position where the hydrogen is pointing down. And on carbon 3, it's going to be pointing down, my methyl, but it's going to be axial. Okay, CH2, CH3, right? The equatorial position will be the one with the hydrogen. Same thing here, okay? So there we go. That's the flip. Now, I have a question for you. Think about it for a second. I want you to tell me, will the equilibrium lie to the right or to the left, the way I have it drawn? What do you think? Based off of what we saw this morning. Would the equilibrium lie to the right or to the left? Anybody have a hunch about that? Yeah, it's going to lie to the right, right? It's going to lie to the right based off of what? 1, 3 diaxial interactions. Look at the axial position over here. There's only one of the substituents that's axial. It's the ethyl. The ethyl is going to have a 1, 3 diaxial interaction with that hydrogen and with this hydrogen. Whereas in this conformation over here, the methyl group is axial and it has a 1, 3 diaxial interaction with this hydrogen here and this hydrogen here, which I didn't draw in. So there's a 1, 3 diaxial interaction here and here. But since a methyl group is smaller than an ethyl group, the equilibrium is in fact going to lie to the right-hand side. Okay? Give me a thumbs up if that makes sense now that you've seen the explanation. Like, yeah, I guess I can wrap my head around that. You know? All right, good. Okie doke. Well, let's take a look at the last section that we're concerned with. Remember that we're going to skip the whole part about polycyclic systems. This is what I was telling you about decalins. So again, when I was a graduate student, I worked on all kinds of decalins and polycyclic compounds and was trying to figure out all the different conformations. Anyhow, if any of you take organic chemistry for chemistry majors, which I know all of you want to take now, so this class is so much fun, you would learn about these kind of systems, but let's just skip it since it's not on our quiz, it's not on our exam. Anyhow, cis-trans stereoisomers, and this is kind of your introduction to chapter 5, really. We're going to start chapter 5 on not until March 3rd, because the next chapter we're going to do is infrared spectroscopy. But anyhow, cis-trans isomerism. Let's talk about it for a second. It says, when naming a di-substituted cycloalkane. So this only works when you have two substituents, right? That's what di-substituted means. So two substituents. We can use the prefix cis when there are two groups on the same side of the ring, and trans when the two groups are on the opposite side of the ring. So look, if I was just to draw this in 2 dimensions with no dashes and no wedges, let me draw it this way. Okay, if I was to draw this and put a methyl group here and a methyl group here, right? Let's go back to last lecture. The longest carbon chain has 6 carbons. So this is some kind of cyclohexane. I give the first substituent the lowest possible number. I could go this way or I could go this way. It doesn't matter in this case because this compound is symmetrical. But this would be called 1,2 dimethyl cyclohexane. Now, if I was to use dashes and wedges, then it gets a little more interesting. So if I was to draw this, okay, and I was to put both of the methyl groups pointing up like this, then you'd have them both on the same face of the molecule. When the two groups are on the same face, they're called cis. So now I say cis 1,2 dimethyl cyclohexane, and the cis is a prefix before the entire name of the molecule. If they're on opposite faces of the molecule, okay, like this, I've got this methyl group going up and this methyl group going down. When they're on opposite faces, we call that trans. So the opposite of cis is trans, and again, you prefix that. All right. Now, it says here at the bottom that these two compounds are stereoisomers. What's a stereoisomer? They differ not in their connectivity, but in the arrangement of the atoms in space, right? If you think about these two molecules, there's two methyls that are next to each other in a six-membered ring. That's all the same. How are they different? It's the arrangement of atoms in space, right? Imagine yourself, right? Picture it. You know, you're standing right here on the molecule. You see this methyl group and that methyl group. They're on the same place, on the same side. Whereas if you're standing over here, you see one up and one below. So it's clear that they're different molecules, right? That means these two molecules, this and this, they have different physical properties. They're not the same. They have different melting points, different boiling points, different densities, different refractive indices, different spectra are produced from these two molecules, and we'll get into that later. It says that since these are six-membered rings, they're best represented as chair conformations. Well, that's kind of debatable. That depends on the situation. Sometimes you might just want to represent them in 2D, but let's take a look at what the chairs look like. Okay, each compound has two equilibrating chairs. If you look at the cis, and this is really interesting, you have the cis 1,2-dimethyl cyclohexane. Either way you slice it, whenever you flip the ring, you've got one axial and one equatorial. No matter what you do, you can flip it till the cows come home, okay? You just keep flipping it for days. You're always going to have one methyl, axial, one equatorial. But look at the trans. The trans is way more interesting. You notice that one of the conformations has both methyls axial, and one of the conformations got both of them equatorial. Think about that conformation where they're both axial. This methyl group on the top has got 1,3 diaxial interactions with those two hydrogens, and this methyl's got 1,3 diaxial interactions with these two hydrogens. So my question for you is, if you have these two conformations, which side will the equilibrium lie to? Will it lie to the right or to the left, the way it's drawn here? And it's not a trick, okay? Exactly, Byron. Yes, of course, it's going to lie to the right. Hard. Okay? It's going to lie to the right. Okay? Scratch that out. Whereas over here, they're going to be perfectly in equilibrium, right? There's going to be a 50-50 mixture. All right? There we go. So it says here the arrow is, this is the lowest energy conformation of the cis isomer. Notice that the arrow is pointing in the middle. Okay? There is no difference between the two conformations. Whereas over here, it's clearly telling you this is the lowest conformation, lowest energy conformation for the trans isomer. All right. There you go, my friends. That covers all of chapter 4. If you just give me like 2 or 3 minutes here, I think I had some practice problems that I wanted to share with you. So just give me 2 shakes of a lamb's tail. While I'm doing that, you could practice your chairs. Does anybody know who Baz Booten is? You always say called a chair. It's like you grab a chair. All right. I have them. Just give me a second. They're in here somewhere. Also, here we go. All right. Okay, so let's see here. I'm going to share it as a docx file. So you can convert it to a PDF if you want. I could post it to Canvas as a PDF if you want, but just give me 1 second. Come on. There we go. The reason I'm clicking a mouse is because my trackpad is dying on my Mac. So here we go. There we go. Correct this. All right. So I just posted them in the chat, and you can open them up and start working on them. And in the meantime, I'm just going to save them as a PDF for my own damn self. And I will, so I can post them on my iPad, and we can take a look at them. All right. Just give me a second here.
And just as a heads up, when people type in the document that you gave us and it opens in Microsoft Teams, it's so that we can all see what we all are typing. So it's kind of like a collaborative document, I guess. So if you want to like work on this by yourself.
No, I just posted it so that you can just download it yourself and work on it at your own pace.
Okay, it's just it opened it in mine, at least in Teams, and I can see other people's initials.
Oh, okay. Well, then just give me a second and I'll post it to Canvas. Just give me 2 shakes of a lamb's tail and I'll do that. So you can...
Wait, no rush. I just wanted to make sure like, if anybody wanted to like do it by themselves or anything that they knew.
Yeah, just give me 1 second. So here we go. Let me try posting it as a PDF. Maybe that'll help. I don't see why you couldn't download that, though. That doesn't make sense to me. But hey, what do I know? All right. Okay, now I just posted it as a PDF, and now I'm going to go into Canvas, and I'll post it there as a PDF, so you can open it up there if you want. And just give me a second.
Yeah, and on the Word document, on the top right corner, when you open it up and there's 3 dots, you could click there and download it, so you can just download your own version of it.
Yeah, I kind of figured that. So yeah, you can just download your own. There you go. So let me go back to broadcasting my screen to you. There. So if you don't have the means to download it, which is no problem, you should be able to see it right now. So you can start working on the first couple of problems, and in the meantime, I'll post them to Canvas. Just give me 1 second. I'll have that done. Upload. There we go. All right. You know, I would recommend that you always start with the practice problems from the book. But these are just extra practice problems that I always just throw together in case we have a little bit extra time at the end of the class. It's always fun to look at a few extra problems just for kicks. Oh, this is going to take forever. Well, in the interest of time, I'm not going to post it to Canvas because I'm having an issue with my Canvas. But let's take a look at this. Okay, let's take a look at the first problem. Just asks you simply, what's the IUPAC name of the following compound? I'll ask my students, did anybody find the longest carbon chain in this one? Or how many carbons are in the longest carbon? Yeah, it's 7, right? There's 7 carbons in the longest carbon chain here. So now if you're really astute, you probably noticed that there might be a couple of 7 carbon chains in here, right? If I start over here, and I just want to double check this, 1, 2, 3, 4, 5, 6, 7. That's a 7 carbon chain. But if I was to use that 7 carbon chain, I have an isopropyl and I have an ethyl. But there's another option, which is, what if I start here? If I have 1, 2, 3, 4, 5, 6, 7. If I do that, then I have more substituents. I have 2 ethyls and a methyl. And remember that one of the rules was, when naming alkanes, we find the longest carbon chain that has the most branches. So if you have more than one chain with the same length, and it's the longest possible length, you take the one that has the most branches. So the way that I've highlighted it in yellow would be the correct way. And if we number it correctly, we have 1, 2, 3, 4, 5, 6, 7. The reason why I numbered it this way is because I have my methyl at the 2 position. So I have a 2-methyl. Whereas if I started numbering over here, 1, 2, 3, my first substituent would be at carbon 3. 2 is a lower number than 3, and we always number it in such a way that we give our first substituent the lowest possible number. So what do we have? We have a 2-methyl. Let's write down what we know. We have a 2-methyl. We have 2 ethyl groups. We have one at carbon 3 and one at carbon 5. So that makes a 3,5 diethyl. And then since the longest chain has 7 carbons, it's a heptane. So when you put all that together, you're going to alphabetize it like this. M comes after E, right? Because we ignore all prefixes except isocycloneo. We ignore the di prefix. And so the name of the compound would be 3,5-diethyl 2-methyl heptane. There we go. Let's take a look at the next one. Longest carbon chain. Did anybody find the longest carbon chain in this one? This one might be a little more apparent. Anybody find the longest carbon chain in this one? Yeah, absolutely. It's 8, isn't it? Yep. If you go from here, 1, 2, so we go 1, 2, 3, 4, 5, 6, 7, 8. We have 8 carbons in a row. If we were to start numbering from here, 1, 2, 3, we have a substituent at number 3. But if we start numbering from here, we have 1, 2, 3. We have a substituent at number 3. So we have to break it up with this substituent. If I was to keep going down here at 1, 2, 3, 4, 5, so my ethyl would be at 5. Whereas if I keep going from the top here, I have 1, 2, 3, 4. I have a 4-ethyl. And so that's going to be the correct way. So I'll erase these numbers and we'll finish numbering 1, 2, 3, 4, 5, 6, 7, 8. So this is some kind of octane. We have 2 methyl groups. We have one at carbon 6 and one at carbon 3. So this is a 3,6 dimethyl. Dimethyl, son of a gun. Dimethyl. There we go. And what else do we have? We have a 4. We have a 4-ethyl. And so I got a lot of dimethyls and diethyls. How are we going to alphabetize this? We've got M for the methyl and we've got E for the ethyl. E comes before M in the alphabet. So this must be 4-ethyl 3,6 dimethyl octane. Dimethyl octane. Like that. Let's try a bicyclo. So here we have a bicyclo compound. I'll give you a second to take a look at it. Well, we have our 2 bridgehead carbons. We have one here. We have one here. Both of the bridges are the exact same length, right? Both of the bridges that have carbons in them, right? We have a 3-carbon bridge here. We have a 3-carbon bridge here. The third bridge has no carbons in it. So the total number of carbons in the bicyclic system is 5, 6, 7, 8. So it's some kind of bicyclooctane, and it would be some kind of bicyclo 3,3,0 octane. So now the difficult part comes, and that's numbering the carbons, knowing how to number them correctly. Now I have to start at one of the bridgehead carbons, one of the carbons I have highlighted in yellow. Now normally you would go with the largest bridge first, but since both of these bridges have 3 carbons, the question becomes, do I start numbering here as number 1 or here as number 1? And the answer is I would start on the bottom and I would go 1, 2, because then I give this methyl group the lowest possible number. If I was to start on the top carbon, the lowest possible number I could give for a substituent would be 1, 2, 3. And since a 2-methyl is lower than a 1-methyl, I'm going to start numbering here 1, 2, 3, 4, 5, 6, 7, 8. I always go from, they'll stay on the largest bridge, and then the last bridge, again, has no carbons in it. So I've got it all set up. I've got a methyl group at carbon 7, and I've got a methyl group at carbon 2. So this is 2,7-dimethyl bicyclo-3,3,0 octane. Could try number 4. The longest chain in here would have 1, 2, 3, 4, 5, 6, 7, 8, 9 carbons. I've got 3 substituents. I have a methyl, I have an ethyl, and I have this one over here. Could anybody name that one on the side?
Is that a sec-butyl?
Heck yeah. Yeah. It's a sec-butyl. Right, and I numbered it in such a way to give the first substituent the lowest possible number. So I've got a 3-methyl, a 4-ethyl, and a 5-sec-butyl. Remember that we ignore the prefix sec, and B is going to come before M, or E, which is going to come before M. And so when I put all that spinach together, I get 5-sec-butyl, 4-ethyl, 3-methyl nonane. All right, just like that. Well, in the interest of time, I'm going to call it quits for today. And I'm going to post the solutions to these problems to Canvas for your perusal. So be sure to try the rest of these and try the rest of the suggested problems that I have posted to Canvas.